Welcome back to Lawrence Tech, where the hits just keep happening. I'm Professor Jim Kearns, and today we're going to talk about the timers on the Atmel AVR chips, particularly on the ATmega 128.4P that we use here in the lab for controller boards. Before we talk about timers, we just need to talk about clocks in general. There's a lot of flexibility in these chips. Get the chip from the factory, it by default is running on an RC oscillator that's built into the chip itself that runs at 8 megahertz, and there's a fuse that you can set to divide that clock speed by 8, and that's set by default, so you end up with 1 megahertz default signal going to run the machine. You can turn that divide by 8 off and it goes up to 8 megahertz. And also, this oscillator is not particularly accurate, but if you want to use it, there's a procedure you can follow to calibrate the oscillator on an individual chip to make it more accurate. Another clock option, selected through fuses again, is a low-frequency crystal oscillator that's designed for use with chips for watches. Do an external crystal oscillator. That's what we use. That's that piece right there. And we run just over 11 megahertz with that. And I think you can run it up to 16 megahertz if memory serves me correct. Then there's, you can synchronize it with an external device through the external clock input. So there's just a number of options depending upon what you want to use it for. And all of these, the clock gets selected through the multiplexer. There's a prescaler option if you want to run the whole chip at a lower speed than the actual input oscillator speed. That goes to the clock control unit, and that sends out the clock to just everything that we're going to talk about. Today we're going to talk about I/O modules, so we'll use that clock there. There's a clock that goes to the analog digital converter, the CPU core, wherever you need. Okay, so let's talk about timers. This is the diagram for a 16-bit timer counter. This is the counter register here, and it will count from 0 to 65,535 because it's 16 bits. And the way it works is we have a clock source coming in. Edges are detected. There's another prescaler here, which will divide that clock signal. Say, for example, we've got an 8 megahertz clock, and we divide that by 64, and that leaves us with 125 kilohertz going into our control logic, which controls the count of this register. Okay, so the advantage to that is by slowing down the rate at which that register updates, we can make it last longer. This register will just keep counting up, and the control logic, depending on what happens, can clear that register, set it back to 0, and it can also control the direction, make it count up or count down. For our example, we're just going to count down. Okay, and what we're going to do in our example is we're going to be setting a value in this ORC 0A for our chip. N is fairly generic because there's potentially more than one of these. We're going to be setting a value in there that we've got, say, that 125 kilohertz update rate. If we set this equal to 124, then basically it will take 1 millisecond for this counter here to go from 0 to 124. And when that counter hits that 124 value here, so they're equal, it sends back the signal here to signal that we've reached the top of our register. That signal goes into the control logic, which sets the clear to set the counter back to 0, and this cycle will just repeat in the hardware without us messing around in software. It'll count up for a millisecond, it'll clear, it'll count up, it'll clear. And we'll also turn on an interrupt thing, so every time we hit that top and do that clear, we're going to generate an interrupt. And that interrupt will just update a counter to essentially count the number of milliseconds since we started up. Now you notice on this diagram there's a whole ton of things that I haven't even talked about, and we're going to leave most of those for later. But these channels are also ones that we could use for pulse width modulation, and we'll get into that at a later date. Here is some of the code. This is just the comments from the top of the header of the H file. I think actually that should be 16. So basically we're going to declare a variable that has a 16 bits. So it'll count up there to 65,535. To use this, we're going to call tick-tock init. It's just a function that initializes our stuff. We'll enable interrupts. We'll use the function tick to reset the timer back to 0 whenever we feel a need to do that. And we'll use the function tock, which will return an 16-bit unsigned integer value of the time since we last commanded tick, and that value be in milliseconds. And the note here is that the timer overflows after 65.535 seconds without any warning or error. It just, like the rest of these library functions, it's just a jumping off point so you guys can do a little work and then, look at it and improve things on your own. This one is a little bit funny. You see some things we don't normally see. This is just the usual, have we run through this yet, so you don't double define things. Include the io.h and interrupt.h because they have all of the stuff that we need to define. When this library function was originally written, we were using an Atmel 32, and some of the register names were different. So what I did is enable me to go back and forth between the two types of chips. I defined these local names to correspond to the AVR defined register names. For the Atmel 32, I would have put the other names that go here for those registers. I haven't included it in this presentation just because it's not that relevant, but it's just something you can do when you go back and forth. Do we comment these out and uncomment the other set of registers? But just be aware, sometimes when you go from an older design chip to a newer design chip, they've made some updates, and some of these register names may change, and you just have to kind of work your way through with it. Okay. We have two control registers. We have that register there where we put in that top value. The timer mask, we'll put a bit in there to enable interrupts, and this bit here will enable the interrupt on OCR0A match. So that's every time we get OCR0A and TCNT0 match, that's when we take this branch and hit that top, and we clear the counter and we generate an interrupt for the rest of the software to run. We talked about the prescale coming in from here. And the amount of prescaling we want depends on the speed of the CPU clock, right? For the 8 millisecond example, if I use a prescale of 64, I get that frequency of 125 kilohertz coming into our clock. If I'm using our 11.05 megahertz crystal, the prescale only has a few discrete values. I'm still going to use 64, okay, to get the frequency in about the same range, but it's not going to be exactly the same. If I'm running 1 megahertz, I'm going to prescale by 8. Essentially, the number of ticks inside that counter are going to be the same between the 8 megahertz with a prescale 64 and 1 megahertz with a prescale of 8. And the value that we put into that OCR0A register, here it's 124, and here it's 124, so both of those will go 1 millisecond. But at this 11.05 megahertz, it works out I have to put in a value of 171 into that register. So if you're changing CPU clocks and you want tick-tock to work accurately, you got to make sure you uncomment the appropriate bit of code here and comment out the inappropriate code. And if if you pick a speed other than 1, 8, and 11.05, you'll have to do a little math to figure out the prescale value you want and the OCR0A value that you want. And the rest of the header file is just the function definitions. The init, the tick, which returns nothing, but it resets that timer, the global variable, and tock, which returns that 16-bit unsigned integer of the number of milliseconds since the last time we commanded tock, assuming it hasn't rolled over. Here's the C file. tick-tock live.h, not a surprise. We have our count here. It's a 16-bit counter. Is the init. So we're going to shift a 1 into control register A. We're going to shift it WGM01. That's waveform generation. I forget what the M stands for, but basically this is what sets up the counter to clear every time it hits the ceiling. Clear on compare mode, so it'll count up, hit that compare, and clear. Set the Prescale bits here. We'll load that value from the previous page into the OCR0A register that sets the top of that counter. And we'll put a value into our timer mask that enables the interrupt every time you hit that top of the register. Okay, that's key to the way this works, because I'm going to go down to the bottom. Because every time we hit the top of that register and we get this timer compare interrupt, okay, timer 0, and it compares to the ORCA0, whatever. This is the interrupt service routine, and what it does is it just increments this tick-tock count, okay, that we call for other things. So every millisecond that counter updates, and anytime you want to read that counter, you just call the function tock, and all it does is it loads tick-tock count into a temporary register, so it then returns that value. And that's really all there is to it. All done in hardware. So once you've selected this value and you selected that prescaler, you set up the interrupts, it's just magic. Your software is doing very little. The only actual regular that the software that your actual code on CPU is doing is updating that tick-tock count every millisecond. So the overhead in your CPU is very low. And that's it. That's all I think I needed to cover. Hope you found this helpful. Catch you next time. Bye.